Okay, well, the red lights come on, so let's get started. Thank you all for being here. This is a special treat today. So, we've kind of reached the end at this point of the convex optimization part of the course, which is really the guts of this course. And then next week and the last week, there's a fairly tokenistic overview or an introduction to basically say there's a whole other world of optimization out there on non-convex problems, which is at least as rich and interesting and diverse as everything that we've done up to this point. So, we essentially don't talk about non-convex optimization at all in this course. So I thought this is a really good time to get Professor Frank Neumann, who leads the Optimisation and Logistics Group in the discipline of computer science now. He's an expert on evolutionary algorithms, genetic algorithms, and things like this on non-convex optimization, to talk about some of this stuff, to give you a bit of an overview of stuff that's going on there. So it's a pleasure to hear from Frank. I partly invited him because I wanted to hear what he had to say about this stuff. If there's time left over at the end, we'll talk about the assignment and stuff and things. Please. Ask some questions and stuff, and take it away. Thank you.
All right, thanks, Louis. So it's really great to be here, and assume that you are mainly from mathematics, right? Okay. So what I try to do is give you an idea where you would apply evolutionary algorithms, what they are, and then also tell you about where it becomes interesting for mathematics or people who are more interested in theoretical stuff and don't want to program at all. Okay. So this is roughly what I will cover. It's just basic heuristics, and I will cover theory. I won't go into multi-objective optimization. So we will only do some very basic stuff here. So that's my first slide, and most probably you can relate to that. So what I give you a function that is mapping from some, I call it search space, let's say to the reals, and you have a subset called feasible solutions. And you would like to find an element out of the feasible region that is maximum. Right? So everyone can relate to that. So what type of problems have we looked into this course?
Just mainly convex.
Yeah, mainly everything is convex, right? So now the question is, what does happen if it's not convex? Or if you don't know what that function is about, and so on, right? So this is essentially the setting that I would like to look into, and that is mainly where evolutionary algorithms are applied. Okay? So what we are doing is we are looking into what I call general purpose algorithms that can be applied without too much problem knowledge. So you don't assume that the stuff is convex, you don't assume anything at all, so still, what can you do? Okay? So, and the question is, why do you need these algorithms? So the first thing is, if you look into algorithms, then you did this in this course, and most of the other courses, if you did computer science courses on algorithms and data structures, so you came across a lot of different algorithms. And for a lot of problems, we know optimal algorithms, like sorting shortest path, minimum spanning trees, whatever you want to do, combinatorial problems, right? So you don't need evolutionary algorithms for that. Right? There's also the class of NP-hard problems, where you could apply these things and you would make them more problem-specific, such that they work on these hard problems. But the main question is, what about a new or complex problem? Okay, so I give you a new problem. I tell you, well, you have 3 days, come up with a good algorithm that somehow presents good solutions for that problem. Okay, so often you don't have good problem-specific algorithms if I give you a new problem. Okay, think of an engineering design problem where you have a lot of parameters that you need to adjust. You can put in some problem knowledge, but in the end, you perhaps have to run a simulation that is then giving you somehow a quality of your parameter setting, right? Okay, so there are certain rules that, certain points that rule out these specific algorithms. If you don't understand your problem, if the quality of solutions is determined by simulations, then what we call that falls into the black box scenario. So you have a potential solution here, you see. This one, the X, you present it to a black box that can be a simulation that is running for, let's say, an hour or something like that, or even days. And then you get a quality. How good is that? Let's say a simulation, how good is that in terms of, I don't know, fuel consumption for a car or whatever you want. Okay? And of course, if you don't have enough resources such as time, money, knowledge, you would like to have algorithms that you can apply to your problem and quickly come up with some more satisfying solutions. I'm not talking about being optimal in any sense. The question is also how good are your solutions compared to optimal ones and so on. So that is usually, in this complex scenarios, what you don't get. Where for your convex optimization part, you essentially get, well, I mean, if it stops there, it's convex, you're optimal, okay? All right. So these general purpose algorithms are often a good choice. So what I want to tell you is how evolutionary algorithms and other stuff looks like, but then also what you can do from a theoretical perspective. Okay? Questions? Go ahead. Okay, cool. Okay, so what we want to do is, so we want to have general purpose algorithms for optimizing a function, f. Okay? So what we need in the setting that I want to present, we need to choose a representation. So how should the solution look like? Let's say, do I encode everything as a binary string? What are essentially the different variables? What are the parameters that these variables can take on, and so on? We need to fix a function to evaluate how good the solution is. Okay? And that might be different from f, from the function that we want to optimize. For example, you would like to have a function that better somehow supports the search, or that is taking into account constraint violations and so on. Okay? And we need to define operators that produce new elements. So the idea is, I have a solution, I present it to my function, I determine how good it is, I produce new solutions, and determine how good they are, and so on, and I keep going. All right? Okay. So the first thing that you could do is local search. Has everyone heard about local search? Okay. So what is the idea? So you have a solution. Think of a bit string. Okay, that's the easiest thing. So I have just a string of 0 and 1s. I define a neighborhood. Let's say for each bit string, the neighborhood is just all solutions that I can obtain by flipping exactly one bit. All right? And then what I do, I start with a solution. I check whether I can find a better one in the neighborhood. If I can, I go for it and just iterate the whole process. Okay? Okay, so that's local search. Start with some initial solution. You just repeat, generate a new solution out of the neighborhood. And I'm minimizing here. So if I can find a solution where the function value is smaller than what I had before, then I go for it until I cannot find any better solution in my neighborhood. Okay? So how should you choose a neighborhood? Let's say you're doing bit strings. Flipping, changing just one bit. Is that good?
Just change a bunch of them into something that's alright.
Well, so the question is, how do you define the neighborhood, right? If I do a small neighborhood, let's say just one bit, then I can explore it quite easily. But the problem might be that I just get stuck, right? So if I have a neighborhood that is, let's say, covering the whole search space, then I cannot search it efficiently usually, but I don't get stuck. So what you usually do is the neighborhood shouldn't be too big, let's say flipping 1 or 2 bits or something like that. And then you can explore that. For certain specific problems, you can even search large neighborhoods by tools like dynamic programming or something like that, right? But this is the basic setup for local search. And you can essentially apply that to any problem, right? So you just need to have a solution, a representation, define the neighborhood, create new elements, and such. Okay? So the design of local searches, so the question is, what is a good representation? And that holds also for evolutionary algorithms and so on. How should the neighborhood look like? So if you have a small neighborhood, you have a small computational cost, but it's more likely to get stuck in local optima. Okay. If you have a large neighborhood, you have fewer local optima, but computational costs are higher. Okay. So what else can you do? Well, you can deal with local optima, where you would get stuck by saying, well, if they are just slightly worse than what I had before, then I accept it with a small probability. Okay? So think of everything where I can find an improvement directly, I just go for it. If I have a solution that is just slightly worse, accept it with a probability that depends on how much worse that is. So it should then be small if I have large inferior solutions. And also over time, I would like to decrease the probability of accepting inferior solutions at all, because at some point I would like to converge. Okay? So what type of algorithm is that? That's simulated annealing. Okay? So you start with an initial solution. Everything looks somehow the same as for local search. You generate a solution out of the neighborhood. If you're better, you just go for it. And else, you have a probability that is essentially exponentially small in how much worse you get. But you are able to accept solutions that are worse than your current solution. Okay? And you iterate the whole process, and at some point you stop. Okay? So you would also then just get your solution. Okay? So these are two things that you can do. So the basic thing in local search, simulated annealing is essentially local search but accepting inferior solutions. Okay? So now, as this temperature Tk is the parameter in simulated annealing that is quite important, that it decreases over time, meaning at the end of the process you are not accepting inferior solutions. Okay. Okay, so evolutionary algorithms. Has anyone heard about that? No? Okay. So the local search and simulated annealing, they work with one single solution at a time, right? You have one solution, you change it, you do it in an iterative way, and at some point you stop actually that solution. Okay? So here the principle is you try to mimic essentially what is happening in evolution. Okay? So what you do is you have a population, and the population just means a set of search points, a set of potential solutions to your problem. Okay? And you have a parent population that produces an offspring population. This is what you're doing by variation operators, so you have something like mutation and crossover. Okay? And then you have selection that selects individuals from the parent and the children to create a new offspring population, or to create a new parent population. Okay, so how does it look like? So you start with an initial population. Let's say you have a problem that you can encode as binary strings. How could you start with an initial population? So give me mu bit strings. How do you do that?
Just pick like a percentage of the whole data set to start with and then go from there. So you just start with like a subset of them?
Well, what you have, let's say, so a solution is a bit string of length n. Let's say a potential solution is just a binary string of length 1000, something like that. Okay? Now, how could you pick your initial solution? One initial solution, you could do all the zero string, so 1000 zeros. You could do 1000 ones. Or if you want to have more variation, you just choose a string uniformly at random, meaning every bit is set with probability 1/2 to 1 or 1/2 to 0. Okay? So this is how you could initialize your algorithm. And most algorithms, they would start with an initial population where each solution is chosen uniformly at random. You could also, if you have already some heuristics or so, like let's say a greedy algorithm that can produce some initial solution, you can also do something like that. Okay? So and then what you just have a while loop that is iterating. So while you have not met any termination condition, meaning you have not exhausted your number of iteration budget, or you could terminate if you have not achieved an improvement for a certain amount of time. What you do then, you produce an offspring population, okay, by crossover and mutation, and you create then a new parent population by selecting new individuals again from the parent and the children. Okay? So all that you need to do for an evolutionary algorithm, essentially implement these modules. Okay? So we already said initial population, if I want to have mu of them, one of them I just get by choosing one uniformly at random. Okay? So what we have to look into is what do we do for crossover and mutation, and how do we do selection. And once you've implemented these things, then you can just run your evolutionary algorithm. So it's very simple. Okay. So the important issues are how do we represent potential solutions? We will just look into binary strings for now. Okay. How does crossover look like? For binary strings, that's very easy, but it can be more complex if you're having more complex representations. How does mutation look like? How does selection? Okay, representation, it should somehow fit to your considered problem. For example, who is familiar with the traveling salesperson problem? Anyone see that? Yeah, okay. So what is that?
I believe it's trying to minimize the distance going between sort of points on the map normally if there's some sales.
Yeah. So you have given n cities, and you have distances between them. You start at one city, you have to visit all the other ones and come back to where you started. Okay? So you could encode that as a binary string, right? Because you can encode everything as a binary string. But most probably you want to go and encode it as a permutation of the cities, right? So it starts somewhere. I just turned back. Okay? So the representation has to fit to the problem. For the traveling salesperson problem, if you're traveling around, you don't want to do binary strings. Anyone familiar with the knapsack problem? Okay, so that is just a problem where you have to pick elements, okay, that have a certain profit and a weight. And to pick elements, most probably a binary string is something that is good because the 1 tells you I picked an element and the 0 tells you I'm not picking an element. Okay? Yeah? So the representation has to fit to the considered problem. So usually what you want to do, a small change in the representation, like flipping a bit, should not change your overall solution a lot. Okay? And often this direct representation, let's say, picking elements, like in the knapsack problem, and decoding that as a binary string, that works quite well. Okay, so what we do now is we just look into the search space 0, 1, meaning all solutions that we're looking at are bit strings of length n. All right. Okay. So crossover, 2 bit strings. So I give you a bit string x and bit string y, and you should design crossover, meaning you would like to produce a new individual from that bit string. Okay. Any idea how to do this? No. So what you want to do is you want to inherit essentially information from your bit string x and from your bit string y to produce a new bit string z. So if you look into, let's say, a position I in your bit string, and both have a 1, what could you do? Do you want to put a 0? Keep a 1. Okay. So what does happen if at a position you have a 1 in one individual and in the other one a 0? Yeah. So now, if you put these 2 things together, you have something what people call uniform crossover. Okay? Okay? And the other one is 1-point crossover. Let's look into uniform crossover first. So you're given 2 individuals, x and y, and you should produce a new solution z. Okay? So at position I, for the new individual, if they are the same, so if they are both 1 or both 0, you just copy whatever there is. Okay? And If they are not equal, then just choose a 0 or 1 with probability 1/2. Okay? So this is what you said, right? Okay? So the other one point crossover, what is that doing? So you have two bit strings, x and y. You just decide on the cut position, okay? And you take the first part from the first bit string x, and it takes the second part from the bit string y. Does it make sense? Well, I mean, the question is, does it make sense for your problem, right? But you can do that, right? So it gives you, from the solution x and the solution y, it gives you another bit string. Okay? So what would happen if solutions x and y are just permutations of n numbers? Could you do the same? Well, so if you we have them.
Yeah.
I'm not sure.
You can erase that.
Yeah. Okay. Okay. You can't see that.
Yeah.
Okay. All right. So.
You can wheel it. Actually, you can wheel it back over here.
Okay. So 1, 2, 3, 4. That's permutation, right? 4 numbers. So that's 1, 2, 3, 4. Okay. All right. So the other one is 4, 3, 2, 1. Okay. So now, if I just cut them, say I cut them here, then I get 1, 2, 2, 1. Is that a permutation? No. Okay. So 4, 3, 3, 4. So okay. Right. So that just means, and choosing these things uniformly at random was what you also did. Okay. So that means, depending on your representation, you have to think about, well, how should crossover operators look like? Okay, for binary strings, that's very easy in this way. But it's not, if you have another representation, then it might be different. Okay? So, mutation. Mutation is, you have one solution, you produce a new one. Okay? Just by doing small changes. If you have a bit string x, how do you produce a new solution then? Huh?
Just times it by a random number?
The bit string. Well, and think of, you have a string of 0 and 1s. How do you change it slightly? I pick a position and I just flip the bit. Right? Yeah, so that's the easiest thing. Okay? So flip one randomly chosen bit. Okay, you can do this. You could also say flip each bit of your current solution with probability 1 on n. What's the difference? You are math people.
Expected sort of results the same, I guess.
Yeah, yeah. So in expectation, you're doing the same. This one here, can it flip 2 bits?
No.
This one?
Yeah.
Yeah. Okay. So what is the probability of flipping 2 bits? Yeah, so it's at least a constant probability, right? So there's a constant probability in the asymptotic sense, and it's large that you would flip 2 or 3 or 4 or 5 or even 10 bits, right? So that one here is very local and would get stuck in local optima easily. Whereas this one, even if you have an arbitrary bit string of length n, and I would like to target another bit string of length n, no matter where it is, what's the probability to jump to that other bit string, where it's at least n to the power of minus n, right? So, because in the worst case, you just split every bit. So this operator is still. Okay. So in selection methods, this is the last thing that you need to do. Think of, you had your parent population, you produce an offspring population now by crossover mutation. Now you need to select. So one thing that you can do is fitness proportional selection. So each individual has a fitness value. That's the function that you would like to optimize usually. And let's say we are maximizing. And this is also where your function comes into play. Right? So I haven't talked in any sense about where your function that you want to optimize is coming in. It's not coming into mutation or crossover. it's coming into selection. So you can do, if you want to select one individual, you could do this proportional according to the fitness values. And if you need new parents for the next generation, you do this just mu times, right? And then you have your new parent population and you can iterate. You can do mu comma lambda selection. Mu usually stands for the parent population size, lambda for the offspring population size. Okay? So mu parents produce lambda children, and then you select the best mu individuals from the children. Okay? You totally forget about the parents, right? This one is not looking into the parents at all. So what's the drawback? You have a good solution, and then let's say you just produce one solution. You have one solution that produces another solution. Does it make sense?
It could get worse than
Yeah, but it's also, you have a current solution, and no matter what is happening, I always accept the next solution that I create. Right? So it's giving me not any direction at all. Okay? Because every time I produce a new solution, I just accept it. So what you need to have is that this lambda is usually larger than the mu. Let's say the mu is 1, and you always produce 10 solutions in that neighborhood, quite close to that, then one of the 10 should be somehow good. Okay? And in this way you can optimize that. If you don't want to lose your best solution, you do something that is called mu plus lambda selection. You have mu parents that produce the offspring, and then you select the mu best individuals from the parent and the children. So you can never essentially use the best solution. Okay? That's most probably the more common thing that. Okay, let me see. Okay. Okay, and here are two very simple algorithms. So one that I call a 1+1 EA, that's a 1+1 evolutionary algorithms, and people studied that for the last 25 years quite a lot in the context of mathematics. So you choose a solution uniformly at random. You produce the new solution by flipping each bit with probability 1 on n. So on average you flip 1, you're allowed to flip none, you're allowed to flip 10, whatever, right? You replace the old solution by the new one if you're not worse with respect to fitness, and then you just keep going, okay? So randomized local search, the difference here is just that you produce your new solution by flipping exact one randomly chosen bit. So this one can easily get stuck in local optimisation, okay? Okay, so, and now let's turn a bit into what can you do with respect to analysis, okay? So you can apply them in many different settings, right? So no matter what complex problem I give you, you choose a representation, crossover, mutation, fitness evaluations, you just run the algorithm and you get some results. If you want to look into that from a theoretical perspective, you will see that it all relies on random decisions, right? So usually the initial solutions are chosen uniformly at random. Mutation is doing something at random, so you would treat them as randomized algorithms. Have you looked into randomized algorithms during optimization courses? For, I don't know, MaxCut or something like that? Okay.
Only stochastic gradients.
Okay, all right, okay. So if you're looking into that from a theoretical perspective, and happy if you want to do projects and find that interesting, that area, talk to me after this. So what we've been interested in is looking into computational complexity on example problems. So we look into combinatorial optimization problems and said, well, how long does it take for an evolutionary algorithm to produce an optimal solution? Or how long does it take for the evolutionary algorithm to get a solution that is a factor 2 approximation, or whatever, right? Okay, so what this area is doing, runtime analysis, it's looking into this black box scenario. So you have a solution, you present it to the black box, and you get your fitness value back. And you measure runtime just by the number of fitness evaluations. So how often do I have to call that function f to get a good solution? Okay, and then, as we usually do that in computer science, you consider time depends on the size of the input. So if I have bit strings of length n, I would like to have an upper bound on the one hand saying this algorithm solves that problem in time O of n squared, or O of n cubed, O of n log n, and so on. Okay. And you can look into optimal solutions for simple problems if you want to understand the working behavior. You can look into good approximations for NP-hard problems. And the interest is the expected number of fitness evaluations. How many iterations do I have to do in expectation to get there? Or sometimes problems are that you fail with a small probability, leading to an exponential time with that small probability. This doesn't mean that the algorithm is not successful, because you could just restart your algorithm, and then you would look into the success probability after a fixed number of steps. Okay, so if your algorithm is with probability 1/2 successful after n log n steps, but takes exponential time with probability 1/2, what would you do? You just run it for n log n steps. If you're not happy with that, you just restart again, right? Okay. Okay, so let me spend perhaps the last 5 to 10 minutes on how would you look into that if you're analyzing evolutionary algorithms. So you initialize this 1 plus 1 EA. As I said, you choose a solution uniformly at random. Okay? And that means you set, for bit position I, you set the bit to 1 with a probability 1/2 and to 0 with probability. How many 1s and how many 0s? Hmm? Roughly. Expected. And what is the probability of seeing 75% of 1s? Give me a probability. So in expectation, we have n half, right? 0.75 times n, do we think that's in the order of 0.1? Much smaller? Any? Okay, let's do this. Okay? So the probability setting the bit to 1 is equal to the probability of setting the bit to 0, right? Okay. So what we can do is we can calculate the expectation, and I think you can all do this, and that is n half. This is what you set. Now the question is, how much do we deviate from the expected value? Okay. Who has seen Markov's inequality, Shannon bounds, and that stuff? Okay. So then, let me just tell you something, because it might be of general interest. Okay, so Markov inequality tells you what is the probability that I exceed the expected value by a certain amount. Okay, our expected value was n half, right? So if I put this as, let's say, equal to 3 on 2, then I get my 75%, right? Okay? So the probability you have at least s times n half, that's the expected value here, 1 bit, is at most 1 on s. Okay? So now we can, for this example, I choose a bit string of length 100 uniformly at random. The expected number of 1s that I see is 50, right? Okay? So if I set s equals to 3 on 2, then the probability that I see at least 75 1 bits is 2 on 3, right? 3 on 2, 2 on 3, right? Okay. So, does that feel about right? Do you think with the probability 2 on 3 you see 75 bits if you do that experiment? Should be much more smaller, right? So if you think of the binomial distribution is essentially in the middle around n-half, and it's highly concentrated. Okay? So what you can do Chernoff bounds. So our initial bit string is we set every bit with probability 1/2 independently of the others to 1 or to 0. Okay? Yeah? So let's say you have these independent random variables, and the probability to set it to 1 is 1/2. Okay? And then you look into the sum of these random variables. Okay? So what Chernoff bound tells you is that you are very close to the expected value. So I could plug in a delta here that is quite small. Let's say I just go 1% away from the expected value. Let's say usually I would see 50%. In the asymptotics, it's highly unlikely that I see 51%. Okay? And this is what this is telling you. So what you're putting in these constants, and then you get the expected value in the exponent, so which means that it drops rapidly. All right. So what I can do is I can do the same calculation with my 75%. Okay? So what I do is I have the expected value here, that is n-half. I plug in delta to 1/2, which means that it becomes a 3 on 2, as we had for Markov. And then I plug in these things, and then Chernoff bound tells you the probability that you see at least 75% is 0.0045. Okay? Yeah? So these are essentially, I only show you this because these are tools that you would use to analyze evolutionary variables. Okay, and that is much better than Markov inequality, right? So the bound it's much smaller. Okay, so and you can put this into asymptotics. If n is going big, then the probability, it just drops. So the algorithm starts with high probability with a solution that has roughly n-half 1 bits. Okay, it's not just an expectation, but it's with high probability. And then now assume that your function has a unique optimum. So you have a bit string, and let's say the all 1 string is the optimum. Okay. So, and I run my 1 plus 1 EA, so it's flipping in each iteration, each bit with probability 1 on n. In terms of order of magnitudes, how long does it take to reach this optimum? And I just want to have a lower bound. N squared, n log n. Any idea? If I start with n-half ones, and I just flip exactly 1 bit, you need to do at least n-half steps, right? Because I can only flip 1 bit. So most probably it's not changing a lot if I flip an expectation 1 bit, right? It's probability 1 on n after everything. But it's a bit more. You need at least n log n steps. And why is that? So you have your initial solution, this is what we said, it's close to n-half 1 bits with high probability. And then you need to collect at least, if I have at most, let's say, 2/3 of the 1 bits, I need to collect at least n on 3 1 bits, right? Do you know that the coupon collector problem? So you're buying coupons, let's say, I don't know, for L players or something like that as a kid. You just buy these things, and then you get a new one, and you would like to get all of them in a certain album or something like that, right? So I'm not sure whether we do it online or something like that. But then the last flicker that you would like to get that takes the longest amount of time if you choose things uniformly at random, right? And this is what slows everything down. So, so this is also the last thing that I want to show you is, so think of that problem. I give you n coupons, choose in each trial coupon uniformly at random, and let x be the random variable describing the number of trials such that you have chosen each coupon at least once. And for the bit string, if you have n on 3 zeros, you have to flip at least each bit once, right? Okay? So what this is telling you is that you need something like n log n steps to flip each bit once. And that would also give you for your 1 plus 1 a lower bound on how many iterations it takes. Because if you have the all1 string as the optimal solution and you have not flipped a 0 that was in the initial string to a 1, then you cannot obtain the optimal solution, right? And this is where there are calculations that you can just plug in, and then it tells you you need at least n log n steps for the algorithm. Okay, and I think I'll stop here. Yeah. So if you want to know more, I give Luis the slides with some other methods around analysis of evolutionary elements, but that's essentially unless you have questions.
Any questions?
Yeah.
How do you decide when Markov inequality isn't useful and the bound is useful? Like at what point do you go, oh, or do you just always use the bound?
No, well, look, so there, as always, the question is what are your assumptions, right? So Markov only assumes that you know something about the expected value. Chernoff assumes that these random variables are independent, right? So Markov, it's much wider way you can apply Markov. Or you would go into, if you know something about the variance, then you would go and apply Chebyshev, right? Yeah, so as always, check the conditions, what is happening to your process, and then think about what you can apply, and then you would like to go with the strongest tool. Right? Okay.
So I have a question. So I guess the genetic algorithms here arose probably because there was kind of a nice analogy with natural selection,
Yeah.
partly, and then it's proved to be useful.
Yeah.
It's
Yeah.
been demonstrated to be a pretty good algorithm. So people studied it
Mm.
and things. But how do you discover new algorithms here? Like, how do you know or figure out what's going to be a good new algorithm? There's kind of no reason why generic algorithm should be good. But how do you go about that search for new algorithms?
Well, so you're right. You're coming. Essentially, it's coming from the 60s or 70s, and it's taking this analogy and putting that into an algorithm, right? I think so. There are a few things that make these things work. So one is that you have a random component that is producing these new solutions. The other thing is that you somehow have a set of search points that is trying to prevent from going into local optima. And then it really doesn't matter how you call the algorithm. It's more like it is following that scheme. So people used to say, well, we just call it randomized search heuristics. And then the emphasis is more along these lines, what I was talking about in terms of theory, just saying, well, you're having essentially algorithms making random decisions. How good would they be? And can you solve problems with them? And then also simulated annealing fits into that, right? And or randomized local search or whatever. So I would not go too much by this evolution principle. It's more like, okay, so it fits into AI and all of these things, and this is where it has a name from. But effectively, when you have a new problem and you design an algorithm for that, you think of, well, do I need to have a large population size, or is it better just to go with one solution, improve it over time, because the population would also slow down your whole process. So you need much more fitness evaluations to to get started somehow, right? So I think it's mainly just taking this population base, working with more solutions, and then just putting randomization on top of that. And you want to make mutation and all that stuff really targeted once you try to solve your problem, because just flipping a bit or something like that is not what you usually want to do if you have more insights what's going on. Yeah. Okay. If you're interested, so we are doing a lot of things on combinatorial problems, not TSP, but some other more complex problems, where we would essentially then design operators. We're looking a lot into how do you relax, let's say, if you have a constraint problem, how do you relax a constraint into the additional objective and then do this as a multi-objective problem? And you can prove a lot of nice things about these things, because that gives you different pathways of solving an optimization problem. So for example, there comes a greedy component in there, which often gives you good guarantees. There's, of course, always a local search component in there, which gives you good guarantees, and if you plug everything together, then you get something that is performing good from a theoretical perspective, but also performing well in practice. And there's often a large gap between algorithms being good in theory and algorithms being good in practice.
Yeah. Cool.
Yeah.
All right. Well, unless there's any other questions, let's make another clap.
Okay. All right. Thanks.
Yeah, maybe we'll stop there. So please come up and ask questions. If you have them, I'll put the slides up on my evening as well.
Yep. Cool.
Thanks, everyone.
Email you sent out the other day about the internship.
Yep.
How much does that apply to a Bachelor of Science, or is it only Bachelor of Mathematics?
Oh, yeah, okay. So you get credit for a maths internship course.
Is that in the applied maths section?
It just has a
okay, yeah.
So yeah, I mean, if you want to credit, so email I don't know if science internship. If that helps you.
Yeah.
I don't know if they have and things.
Hi.
I was going through one of your papers. You
I was looking at it, and
developed some operator to just optimize.
Sciences or
I don't remember exactly.
So trying to
Yeah.
Use some operator to just enhancing the performance of any algorithm. So what base you are using to, are you going to compare with some another algorithm, or it's just the computational complexity you find in terms of time or in terms of iteration?
Well, it depends on what the paper is about.
I think this is very interesting. But
If it's on theory, then it's often getting the runtime down smaller. If it's on application, then of course we have to compare.
application means if you use some real life applications or
Then you compare on benchmarks
in
mostly,
the
right?
benchmarks.
Yeah.
So sometimes if there is one problem I'm working in, that my task is to reducing the cost of the water network design.
Yeah.
So do you think that the time would matter here? Means my results are quite good here in terms of reducing the cost, but the algorithm is taking time. Like if I use the genetic algorithm, it's take like running the same program in 60 seconds, and if I'm using the algorithm which I'm currently using, that it's take like 1 minute and 30 seconds, let's say.
Yeah, the question is what is the quality of the that you get in the end, right?
So somehow it may matter that whether the algorithm is taking more time, it could not be a good, considered as a good algorithm. Can this be a benchmark for judging the algorithm as well? So the question is this.
But the question is, if you are happy with spending one hour, then 1 hour is fine, right? If you're happy to spend 1 day, then that's also fine.
Yes.
It is not that. So why should you use an algorithm that is running for 30 seconds if you need your solution just tomorrow or next week, and you come up with a better design?
Sometimes like that you are focusing on reducing the cost regardless of time. I mean, it is okay if it's taking 1 point.
Yeah.
Yeah,
Yeah.
so this could not be any benchmark to, I mean, it just